So we're here to discuss what is available with Mistral AI and do a little brainstorming of what we might try to do with it. And then we can try to go through, look both at their website, their API, FunSearch, if people have other ideas for inspirational code out there that we can borrow from. We can look at that. So let's see. So just to describe the basic situation. So everybody probably has heard of Mistral as one of the leading AI labs producing large language models, and they're based in France, of course. Francois has very good connections with them, and so we had the idea that we could ask them for credit to use their language models, and so they generously have offered at this point $3,000 worth of credit to use any of their models, and we can discuss later what we can hope to do with $3,000. I think the short answer is that we can probably run 2 or 3 serious experiments with that kind of money. And so it's definitely enough to try things, but not enough just to hand out the credit to everybody and say do what you will. We're going to have to be a little bit more strategic and selective in how we use it. So what do they have? I mean, so you can look at the Mistral website, but I think what I would think is the most likely thing to be interesting for us is their code completion model. And I could share my screen. I don't think I will. I got something that everybody can look up. It's okay. So released May 2024. Well, why don't I share the screen since I'm just kind of reading from it. So
you said CodeStraw, right?
Yeah, CodeStraw. Yeah. Okay, so this is their mistralai.news/CodeStraw, as you can see at the top. And so let's see how many, okay, this is their news item with benchmarks. So this is, trained on code in many different languages, but obviously is going to be better at high resource languages, Python especially. Not so good at lean or theorem proving and so forth, although people have tried for that sort of thing. And they're citing results for the model we use, which is 22 billion parameters. And it's, what they say is it's quite competitive, with the state of the art that other firms have produced. So, okay, we don't need to download it again. It's not outrageous to run this if you have a big GPU available to you. It's definitely something that one could. Mistral is very much focused on open source and providing both services and code and weights. So it's something that we could run, but again, we don't have to do that. We have their API available that should make it relatively easy. Let's see. I suggested, again, I'm hoping there's enough enthusiasm that somebody has tried out their API and can show us an example of that. Did anybody participating here do that? I've I've done this kind of thing, but I haven't tried to do it yet with this. I have a paper with a postdoc here, which used the OpenAI, in fact, GPT-4 API to do economics, multi-agent simulations. So I can tell you from that experience that it's really not that hard.
Yeah, I also tried and it's completely straightforward.
Yeah, that's right. So, so it's obviously the details will be a little different, but probably not that different. I mean, we can go to, yes.
So as far as I recall, like the Mistral API is, so I've been playing with it as well. I have a implementation working.
Right. Yes.
But the Mistral API is very easy to use. I think a lot of these guys model off the OpenAI one.
Yeah, good. Do you want to show us something or?
Sorry, what's that?
If you've been playing with it, do you want to maybe show us a little something?
Well, I guess what I've been playing with it in the context of getting the FunSearch working.
Okay, good.
Okay. Yeah. But so the real challenge, so FunSearch, I have a single threaded implementation, like it works.
Good.
The challenge is going to be building the distributed version of that, so the multi-threaded asynchronous version.
Let's discuss. Again, we have to discuss.
I have some experience with multi-threaded.
Okay. I mean, if we need it, it's something we can do. Now, when we say multi-threaded, I assume we're doing that just to make many APIs.
Yeah, exactly.
Now, I guess the number one question I have is, what does the API call that we're going to use cost? So how many calls can we make in our experiment?
Quite a few. So I've been running for the last sort of 10 minutes or so.
Okay, good, yeah.
And it probably costs on the order of 10 cents maybe.
Per call?
I can't get access to the
10 cents to run for 10 minutes. Well, how many calls did you make?
I probably made a few hundred calls, I'd say. 500 calls. And it's probably 1,000 calls, and it's probably less than 10 cents.
Okay, good. Okay, but that's still it kind of adds up. I mean, for that means we can make 1 million calls with $1,000, right?
So it's 300,000 tokens, costs 10 cents. 300,000 tokens. Okay,
good. And then your calls are FunSearch, I guess the program is not that long, right? The program that it generates is maybe 2 or 3 pages long.
Join meeting. Sorry, I'm trying to join the meeting at 9.
Where I'm headed, obviously, this will determine both the scale of our experiment and it will determine to what extent we need multi-threading or other clever techniques and to what extent we're limited by time and to what extent we're limited by money.
So I think that 22B model can probably fit in A100. So.
Oh yeah, that's right. That's right. We could run it ourselves. I am assured by Francois that if we start getting interesting results, this is just the starting point, and they would be very likely to fund us to go further. So we should regard these first experiments as the proof of concept, to get some kind of interesting result.
Okay. So our goal is to get some signal that there will be something interesting.
Yeah, that's right. I think if they see, especially if they see the prospect of some paper that will attract attention, they would throw it more. Yeah.
Right. I think I should be able to share my screen, hopefully. Yeah. So can we see what's going on?
If you can make it a little bigger, that would be nice.
Not totally. Okay.
Okay, it's okay. That's fine. Yeah, good. Okay.
Right. So I guess I'll just cancel this run. It's pretty. So basically, I've used there's the Google implementation.
Good.
Sorry, the DeepMind. Yeah. The FunSearch implementation that you linked to. There's someone who's basically done a bit of work already to set how another single threaded implementation, and so just getting that working is relatively straightforward. And so, but if you have a look, so here we go. So you can look at for example, the capset problem, and this is basically the prompt that gets fed into the your Mistral model.
Right.
And in some sense, coming up with a new problem is just as simple as rewriting the prompt to.
Right.
fit your problem. So for example, for Salem-Spencer, it's again pretty easy. So you can think about exactly how to set up the problem, but the simplest possible implementation is just is something like what I have here.
Would it be, before you go on, would it be useful for people, for us to briefly review how FunSearch works and what we're doing with the LLM, or are people kind of familiar with that at this point? So just, I mean, the most simple statement of it, in this case of CapSat, is the thing is writing we're asking the LLM to write a program that ranks, computes a score as a function of a vector, something in Z3 to the n, and then it's going, so the language model writes a program that basically is a function that computes a score for a vector, and then the system is going to run that program to use the scores to produce as large a CapSet as it can, starting greedily with the highest scoring vectors. So most of the search, of course, is not the responsibility of the language model. The language model basically is doing a sort of genetic programming step where we give it two of these function definitions and ask it, make another one like that. So the call, as you say, is not that big. It must be. So you're literally doing the FunSearch of CapSet, and you said that you did. You said you did 100 runs for 100 calls for 10 cents, or
yeah, something like 1,000 on the order of 1,000 to 10 cents. Yeah.
1,000 calls for 10 cents. Oh, okay.
Here's an example of the prompt that gets sent to the
right.
To FunSearch, exactly.
That's right. So it even tells it what we want.
Yeah, and so here's the first version is priority v0, which is just it basically tells the order in which you should select the relevant numbers. And simplest possible program is the ordering is basically in the order in which you encounter them. So just arithmetically. Right. So and then you ask it to try and evolve that. And so if we scroll down later, hopefully we should find, here we go. So a few different versions prompted. So here's its response for priority v3, and it's computing some sort of complicated measure of a penalty and a bonus, and then returning all that as the priority. And it's come up with this by itself. It turns out, I think, that this actually didn't work. It didn't extend the Salem-Spencer set more than the simplest possible program. But
okay. Well, this gets into the next question: is that once one gets completions from the language model, what fraction of them even compile and make sense, and then what fraction?
With Codestral, it seemed like quite like, I didn't have statistics for that, but it's most like.
Oh, very good.
Most of them would work fine.
Okay,
so,
that's great. That's great.
So here, that's some of the early ones. But if I click through sort of random, in my 300th iteration, most of these have returned nothing in terms of the error.
Okay, that's good.
But here we go.
And then how many distinct programs, or how many distinct outputs?
That's not a statistic I can usually come up.
Okay. I mean, that's worth checking, but it's again, if they're largely distinct, that's important.
So I think you do something like sort of a temperature, like you start off with quite a high temperature, and then over the course of training you lower it for obvious reasons.
Okay.
And that is definitely implemented already.
Okay. So okay. Well, all this sounds promising. So. It does start to sound like the multi-threading would be useful, doesn't it? So if you did, now you said in 10 minutes, you run it for 10 minutes and you got several hundred calls?
Yeah, on the order of 1,000 calls from just that.
1,000 calls for 10 cents in 10 minutes. So then, well, I mean, it's still not clear that time is the limiting factor. So so that means a dollar takes about an hour and a half, 100 minutes. And then given our budget, an experiment, a run ideally is like $100, $200 or something like that. So I guess there's, some modest multi-threading. If we had like 10 calls going at the same time, that would be what we want.
So one of the bottlenecks is basically, probably just evaluation, especially for larger, here I'm only using Salem Spencer sets of size like 20 basically. And that's probably not enough to actually have any real discrimination. So you really probably want a lot more. And I think, so at least in the FunSearch paper, they had a sort of 150 different evaluators, and I have like 5 or something. So that's when you really want the multi-threading. Like you want each evaluator to be able to run for as long as necessary. Maybe 30 seconds is the cutoff. So that's why. So querying the models, you'll probably be okay, but it's probably the evaluators where you really need the multi-threading.
Okay, tell us what's the evaluator doing? What is his choice?
The evaluator just runs the program on a whole bunch of different inputs and then gives you a score to say, so.
Okay, so actually constructing the list of vectors given the score function.
So here's the output of an evaluator, for example, like actually you can see it here. And the best scores so if you take the numbers from 1 to 20, then the largest Salem Spencer set that the trivial program was able to find was size 8. And then size 24 was also size 8. And size 40, it was able to find one of size 15. Which is the bound.
But evaluator is using the score function to produce a cap set and seeing how big it is. So clearly that's evaluator from the point of view of reinforcement learning or search. Okay, but so yeah, I had wondered this myself. Given the score function, it wasn't clear how efficient it would be to actually produce a cap set from just knowing the score function. So you're saying that's not very efficient.
It's not totally
not terrible, but it's not. That's the limiting factor.
Yeah.
Okay. So can that be multi-threaded? Sure. Well, I mean, in principle, yes. Of course. Yeah. Of course, the lazy way to do multi-threading is just to have multiple processes, if the things don't have to talk to each other. But here we're saying that we have, again, this kind of population genetic thing where we keep the best ones and, use those as our source programs going forward. That's also an ingredient to the thing. So to what extent do the different threads have to talk to each other?
So not actually a crazy amount. So the way they do it in the paper seems to be just like 3 different types of asynchronous workers, which just go off and do that and then come back and sync whenever is necessary. Like it is mostly like it's not that hard. It shouldn't be that hard to get working.
Okay. Well, then let's try to do that. That would be a valuable thing to be able to capability. Okay, so this is what I was hoping. It would not be hard to get this running, and it sounds like you're basically there in terms of getting it running.
Yeah.
Okay. Well,
it's tuning high parameters, like tuning your prompts.
Do you want to share what you've done so far? We can sort of get up for this. Or...
Yeah, sure.
Okay, excellent. Okay, so. Okay, well, we can continue then to think the programming, the more technical side, or maybe we should switch to kind of brainstorming. And what else could we do besides just try to duplicate the same FunSearch? So do people have ideas along the lines, first of maybe a FunSearch, other problems that the FunSearch method might be good at? So what would make a problem a good target? Okay, yeah.
I have an idea. Problem. So it would be a node 3 points in a line.
Yeah.
To come up with the general constructions. The problem is n by n grids. Put as many points as possible in the n by n grids without having 3 points in a line. And the problem here would be to come up with a construction that works in general for all n, and the best known is 1.5 times n. That's a very simple construction, 2 lines of code.
And then the construction generates points.
Exactly.
Okay.
Take 2 hyperbolas in the right way.
Right.
That's it.
Okay.
So very, very simple with codes. So we should be able to find the same construction with FunSearch. One issue with that would be with this problem is that if we just try with the standard FunSearch approach, it's going to give us score functions. And if we start with choosing points greedy according to score function, we're going to skip many, many points.
Yeah.
The final construction will be really hard to interpret.
Yeah, maybe the score function is not the best way to describe those solutions.
So I would suggest that we change the evaluator by choosing the highest score points according to the score function until we cannot choose something anymore, and then stop.
Well, they had to use something like a square function because it's such a huge dimensional space, but this space is not big.
We're still going to evolve a score function, right? So,
Well, I mean, if we don't rewrite the program, we'll be evolving a score function, but it's not that big a change, right? To just generate a configuration and do it some other way.
that is true.
Yeah, I mean, it's true. It's asking the program more of the program, or the score function is kind of a class of programs that you can at least count that it's going to run, and it's not going to, it's true that generating a list of X, Y values is maybe a harder thing, but it doesn't sound so hard.
But if these points are just the solutions to a hyperbola, then it's
Yeah,
really
exactly. Then it's a pretty simple program. So maybe in this case, the direct generation.
Maybe. I'm the only thing I'm confident in is that we shouldn't do the same approach. It's not going to help us if you have a complicated score function and you skip half the points.
Okay. Well, so we can think about possible approaches for that. Now, I guess there's okay. That's an idea. We'll come back to like the details. So so we can make a list of so no 3 line problem.
Yeah, the lower bound is 1.5 times n, and it's really just 2 lines of code.
Okay, good. Okay, do people have other ideas of? Again, it seems like combinatorial optimization. This kind of thing. This is what FunSearch is designed to do. Any ideas? Well, let's just brainstorm again. They don't have to be good ideas. So, we talked about a few problems that were of this.
Yeah, I think several problems that we consider this week would be good fit in similar ways.
Can I ask just a very question? Sure.
Yeah.
So especially those who were very involved in, like, for instance, the largest isoskills triangle 3 problem. So do you have some experience how these actually behave for like using FunSearch, or have you tried? I mean, there's a lot. So kind of these have the same scheme, kind of trying some sort of points that satisfying some properties, and then you can basically train and find some code which gives you the priority function, which actually you can use to build up. So kind of the same. Do you have any experience in FunSearch with these?
I'm trying to remember if Jordan said they tried it.
No,
I didn't get any result. That was the thing. If they tried it, it didn't really work. You don't think they even tried it?
I'm confident Jordan hasn't tried this one.
Yeah, okay.
As of like a few months ago, nobody has tried it on that problem.
Yeah, nobody's done much with FunSearch. This is, that's certainly a reason why to try.
Yeah, absolutely.
Okay.
One thing that's not clear to me from the paper is how much they had to spend on their
Oh,
evaluation.
yeah, they don't say. I looked carefully for that.
It's a concern. And also, of course, how long they spent trying to tune it to make it work.
Yeah, well, that's right. I mean, that's the biggest open question. I mean, maybe we can find out from somebody. I mean, I think I asked Jordan this, and he didn't really know. So,
Yeah.
I mean, we'll just try. I mean, that's why we're going to try a variety of problems and not just CAPSAT. But that's right. The paper's not totally open or reproducible because of that. But they did provide their code, so let's just see what we can do.
Did you guys manage to reproduce the CAPSET results, or are you still very far from it, or how?
They just started, right?
Yeah.
They haven't done much.
Is it like a big project to reproduce that result, you think?
Well, that's what we're wondering. I mean, my guess is, yes, my guess is that they have, months of GPU time, I mean,
Yeah.
they were trying hard to get a record,
Yeah.
so. I mean, to reproduce it for a small case, that we can do, but, so.
Yeah, maybe the question will be just to run the simple FunSearch and see for small dimensions, how well does it do?
Yeah, I
Like,
think
you
that
know,
we should
after
do
1
that.
hour.
Yeah, exactly. We should do something like that. We should do enough to reproduce it and kind of compare where, and leave the CAPSET at that. Yeah, so, okay. Okay, well, I mean, we can all, again, there have been several of these combinatorial optimization problems that we've already discussed, and we can make a list and try to think, both this question of should we do it using a score function, or should the generating program and take some other form and try to estimate, just to do some kind of experiment, how much would we have to spend?
I think the score function is very good at using good construction for one particular size of n. If you want something that we can then generalize by hand, we want
Okay,
something
well,
that
is that intrinsic in the idea of score function, or is it just, maybe there's some way to solving that within the
score function. We need the final output to look like the program. If we end up skipping half of the points that the program suggests to us in order, then we won't actually understand what the construction is.
Okay, that's certainly a consideration. I mean, again, the first thing I would have said, and I did say, is that if you're constructing by pulling things out of a very high dimensional space, you're sort of forced to this score function. And if it's not a high dimensional space, we have many more options. I mean, I guess you can generate things in a high dimensional space, but that's a much harder problem.
We can do halfway between the two methods. We have a score function, and we're allowed to make some mistakes, but not too many, and then the final construction will still look like the score function in a way, and maybe we can then still look and understand it.
You say if the final evaluation doesn't correlate to the actual score function, then what's it searching on? But I mean, it's sort of still searching. I mean, it's not like the language model knows that much about the score functions. It's just taking two functions and producing another function like those.
Yes, but if in a problem we want to eventually generalize our constructions for all.
Okay, there's the question of does the construction work for many ends? But in general, that's hard, right? I mean, depending on the problem, there might not be much relation between the constructions for different ends, right? I mean,
in the tree line, there's a 1.5 times n construction.
In that case, it is. Okay. Yeah. So
it depends on the problem.
Okay. Yeah. Okay. So that's a consideration.
Or at least all primes or something.
Yeah. Right. Okay.
Can I have a very quick other question?
Please.
Just really because I don't really know the FunSearch experiences so far. So is there any other instance of using this sort of at least some experience with producing another sort of output for the priority function? It's just not learning a code which produces a priority function, but any kind of other sort of insight into some construction, say whatever, like a Boolean expression or anything else. So all the existing examples for FunSearch basically produce priority functions.
Well, I think what they reported in the paper is all priority functions, and I think from Gordon's talk, they tried some other things that did not have much success with the other things, but they didn't report that.
I don't think they tried that much. So
yeah, they probably didn't try that much. That's right. I mean, certainly we can try anything, and I guess again, it should be some kind of robust specification where it's not some very tricky thing to write a program that produces a sensible output. And as long as it's robust, then yes, let's try it.
And is there any direction, trying to kind of train more than one, finding more than one code and which kind of and combine these together to give something, or is this
You mean like
something
score
we've not
function
tried?
plus something else, or when you say combine?
What I mean is that kind of different kind of priority functions, and then they somehow combine these together to
I mean, that's sort of what it's doing. Right?
the final one.
We have this big pile of basically priority functions. And then what the language model does is you give it a couple of them as the prompt, as it's like few-shot learning. And then it produces another one like those.
But it's always told to not change the program too much, so it cannot like properly combine two codes, I guess.
But it is this, it is the basic stuff,
But I think Gregor was suggesting to take two programs that are completely different and somehow really mush them together.
But programs that are computing different things, not just priority function or.
Not sure.
Yeah.
Yeah, I mean, we could try maybe to get.
Yeah. Okay. I'm just.
Yeah, that's right. I mean,
And one more question, but this is just a final because this is just naive question. Sorry for this, but kind of according. I mean, my understanding is right now this we have this space of all, we can actually move somehow the space of short Python codes,
right.
and in some sense we kind of we have a that's the move how we select like a code. We generate a few codes and we test using the score function whether which one is the best, and we keep some sort of the best ones and then generate new ones. That's the strategy, right?
Okay, that's the strategy, yeah.
And I also see that there are some sort of more sophisticated way they do kind of to cover more of the space. They have these islands actually, and then they they kind of select not just randomly one island and then select from an island and they generate the code from there and so on. But is there some, again, just a question, this is purely out of curiosity, like kind of, is there any more sophisticated ideas actually to make some more sophisticated move in this space of Python codes, let's say, sort of, I would like to go in this direction using some sort of a gradient idea or something like that. And I'm sorry, this is a very, very general and naive question.
That's a reasonable idea. Does anybody have any comment on it?
Mm-hmm.
I mean, the first thing, of course, that comes to mind is that Python code is very bad from that point of view. But to compute the gradient of a program with this unknown direction.
Yeah, sure. You could build like sort of a network
it's still a good idea. It's still worth trying to think of do something.
Yeah.
I mean, I guess you could have not just a single score function, but you could combine, take a linear combination of score functions, and then those coefficients would be accessible to what was done.
Yeah. Okay.
I have a comment that's not exactly on that, but it's about the Salem Spencer thing, which we thought might be a good test ground. There's obviously the danger that, if we choose that to be our evaluation problem, that we're hoping to reproduce the bare-end construction. That's definitely in the training set somewhere. But obviously, empirically, clearly, Codestral has not worked out that this is the Salem Spencer set, even though it probably could quite. I mean, I actually think I say the word Salem Spencer, so it probably could work it out pretty easily, but it doesn't manage to do that. So the question is, are there any more niche problems that are less likely to have coverage on Wikipedia that we could test it on, where the answer is known, or at least a good answer is known?
Well, right. I mean, if the, I mean, we're sort of looking for problems where we can get some new record, and so even if the solutions, some useful solutions there on the web, it still didn't produce a record, and so I don't think that's a problem if it can find the relevant stuff on the web, but. I mean, we should be thinking about a broader class of problems. I mean,
It was just a comment on the Salem Spencer thing. That was it.
Right.
I think, for example, Jordan's isosceles problem is definitely not on the web.
Right.
and we have records, so that's easy.
Okay.
But we can easily come up with 5 other similar problems. That's
Right. Otherwise, let's make a longer list and then try to think a little about, what would make it good for FunSearch, before we commit a lot of effort to one of them. Okay, so, but yeah, no, I mean, for example, what I was just saying, you could imagine a scheme where you have several components of the score function, and then you do have the ability to learn those coefficients with what you're combining, and conceivably is full idea or something else where you do have parameters that could also be optimized. Maybe just parameterize score functions all the way, against asking more of the language model to write them.
I would suggest, and you can disagree, that we try many problems instead of focusing on doing things.
Yeah, that's right. Okay, so that's right. So try many problems and then focus. So that raises just the question of how many trials do you have to do to get any sense of whether, I mean, certainly at this stage of considering the problems, we should consider many problems. We should just make a pretty good sized list. If we get like 20 problems on the list, that would be great. And we can all contribute to it.
Yeah.
And then I guess, so how much running does one have to do to decide if this is working? I mean, again, there's a problem. If we stick to FunSearch, there's how do you use the score function, or do you use some variation of the score function? And then, at least in my mind, again, the first hurdle is, can CodeStraw actually write that kind of function in a reliable way so that most of them compile and make sense? And I don't take that for granted. And so that would be a test that one could do a relatively small number of runs and maybe cut some things out. And
so you mean just checking after a few runs?
Well, I mean, we were trying to do a much harder thing in our multi-agent simulation, but definitely even GPT-4. So we were basically asking the agents to make economic decisions. And so it took quite a bit of work to make a prompt where, even like, 20% of the decisions were sensible, And so, again, depending on how much, effort and how much structure you're putting into your score function or your generating function, it might be an easy thing for CodeStraw to write, or it might be a hard thing. So that's one cut. I mean, maybe it'll turn out that lots of the problems is just easy. And then how do you judge? Well, I mean, there's some next criterion of it should be able to write diverse programs, that all make sense and produce different constructions.
We can check how close we get to the best records after some time. That will give us an indication.
That's right. We could try a small version of the problem. And so we could probably do enough tests, to spend $10 or $50 on one of them and decide how promising they are from that. Okay, so
one test we could do, but this is probably very ambitious because people have tried, or people have tried to improve this a lot, is the triple L algorithm. So finding shortest vectors.
What are the three? Lenstra,
So the triple L reduction. This has of course tons of applications.
Yeah, that's right. That's a huge kind of research field in itself.
Yeah. So if FunSearch could find something.
Shortest lattice vectors, that kind of thing.
I mean, all the ones that FunSearch have formulated is in terms of finding. That'd be quite hard.
I feel like the best problems to start with are ones where the best known constructions have short code corresponding to them. They're simple to write evaluators for them, so we can quickly just write the framework and just get going with things.
Yeah, we should have certainly something like that.
Yeah. We can have some more complicated ones.
Okay. Well, I mean, it's sort of a plan. I mean, so generate some of these problems. At least we have now a basic code and a basic way of evaluating. In the meantime, people can improve the code and make it multi-threaded, and you can, if you want some credit, continue to reproduce some part of FunSearch. We can give you some credit.
So, if you want to start collecting problems, what do we need to create for each problem? We need to create an evaluator function that takes and input a score, and a score a priority vector, and outputs a number representing how good the construction is. So we can just start creating a GitHub repo.
Yeah.
For each problem, you have one file like this.
Yeah,
It's really straightforward to run it on different problems. I mean, once you
good.
So the only thing we need to write for a new problem is just the evaluator, and I guess skeleton for FunSearch, right?
yeah, it's just one Python file with an evaluator and a solver. Well, with a solver basically, yeah.
Okay, so that's right, we should get started on some, set up this repo and make some examples. Okay, that sounds good. So, I mean, so this is, should we try to think about other types of projects? Do people have any other idea of something we can do? I mean, if we were doing, theorem proving, of course, there's all sorts of directions that one can try to use language models to do theorem proving. That's kind of a different direction.
Yeah, that would be very nice. Can we do reverse FunSearch? So there are some problems where we have the best construction for n equals 100, whatever, but we don't understand it. And us get somehow.
So interpretability. So the construction came out of like some transformer or something.
Yeah, exactly. It came out from some really ugly code, some searches and brute force and everything. Can we get FunSearch to approximate it with code somehow, and then we write the code, and the score of the code would be how similar it is to the construction.
Okay.
So that could be a fun thing, right?
Okay, so interpretability, basically, we have this interesting function.
Assume that the best construction is nice because maths is nice, so that's often the case.
Right.
That means that there is a short description of it. Let's try to find a program that generates this construction.
So that's probably pretty, you can do that evolution to some extent with Codestral already in some form, because it has a Kolmogorov complexity penalty, which you could just ramp up, initialize from a certain program and then.
But how do we tell the language model anything about the function that we're trying to fit? I mean, of course, if we don't tell it, we can implicitly tell it the way that. I mean, so in the FunSearch, we're only implicitly telling it the function we're trying to optimize by selecting, the score functions which did well, and so we're imagining doing the same. We're imagining. Yeah, I mean, if you so that my initial reaction would be to say that works much better for optimization, where you're just trying to maximize one thing, than for fitting, where you have to. But maybe once you're in the neighborhood, where you're optimizing the error, it's conceivable. I guess once you get anywhere, well, I mean, you could just say it's just another high-dimensional space. Why not? But I mean, the high-dimensional space again. It's just kind of like if you're thinking of writing the program that computes the function, that's kind of analogous to writing the program that produces the capset or something, right? So it's just this very high-dimensional space, and the space of programs is very complicated. And I guess, I mean, maybe let's see. I mean, again, it's sort of. I mean, symbolic regression is sort of like this. People do genetic algorithms for symbolic regression, and then the general experience is that it works very well with functions of one variable, and kind of usable for functions of 2 and 3 variables, and that kind of runs out.
I see. So you're saying this wouldn't work well because we would.
The function space is just too complicated and big, and we're kind of feeding in the information to it indirectly.
Yeah, you're not actually showing the construction directly. You're just scoring.
Yeah. So.
Well, we could input the construction as in the prompt as well. And
I mean, I think it's worth trying anyways, but I'm not a priori that optimistic if it's a function in a high-dimensional space. Maybe it's a function.
It's just another idea to try.
I mean, we could try it on a test case where we know there's a simple function and see how well that works.
Absolutely.
Yeah.
The 3 in a line, perfect.
Yeah. Okay, that's probably worth trying just as an experiment. let's see, what other, we have other general ideas how. Man, I mean, again, things where we could write programs, have the language model, write a program and explore the space of programs. So are there other pieces we can make for that? Something where there's some kind of, it's possible there's a program that can do a good job, and it's just this intricate kind of search problem. A different, I'm not saying we should do this, but another kind of related project, which I can send you references, trying to generate all the sequences in the OEIS, the online encyclopedia of imagery sequences. So there is a series of papers, a group in Europe that generated something like, they had an automatic system where they were able to find programs to generate like 100,000 in most of the OEIS.
So the input is one particular sequence, and it has to write a code to find
Yeah,
sequence.
so
So it's kind of dependent.
I think that's right. I think your input sequences and it kind of again combines. It's just codes that it already knows to try to come up with a new code. And I think it doesn't use large language modeling. It's just more.
So it's similar to this interpretability.
Yeah, that's right. That's the thing, which is maybe more similar to what you're saying. So they did have some success. I mean, it's again one kind of sequence, but maybe that's the looking at.
We can try it with sequences where it's only computed up to a certain value, and we don't know the next values. And
right.
Anyway.
Why not?
Yeah, like at least I'm aware of Joseph Urban.
Yes, right. That's what I'm thinking of. Joseph Urban and Thibaut Gauthier.
Yeah, but he had a very fixed structure for the algorithms. So the question
right. They used a special language. They didn't write it in Python. They did this kind of code language that the thing generated. That's correct.
So one could look at some examples that they matched well and see how does something like LLM match to generate some code. Because they were really fixed. They basically said that the only code can only have certain like if statements, and some it was always very, very simple. So I don't know, could be interesting examples to try to see if we can recreate also that, but with LLM instead of.
Yeah, that's right. Okay. Other ideas. We have a main project. I think at this point we have an idea of how to get started. So should we just start on that? Other suggestions? We'll sure have another meeting like this next week. We'll keep to discuss our progress.
So how do we completely get started?
Okay, well, I think Kit is going to make a repo that has his running implementation. Hopefully has instructions for how to put in a new evaluator, a new class of a new problem.
If you have one or two examples, then we can just do the elementing and just imitate those examples.
Yeah, that's right. And
and we just start pushing more and more problems, like 20 problems.
Yeah, and then we can find a scheme to run them long enough just to see if it seems promising at all. And then we'll decide which ones to carry forward.
Absolutely. We should have some description about each problem, just a paragraph. It's enough.
Yeah.
Should be fun.
Yeah.
Mm-hmm.
Okay, so So, I mean, if we think we can get started quickly, we can schedule a meeting early next week to, discuss where we're at.
I think it's a good idea.
Okay, well,
I think let's do.
okay, good. I mean, Kit, does that sound good?
Yeah, great.
Okay, so maybe even, Monday, Tuesday, maybe Tuesday is a good.
Do you think you will create the repo today or?
Yeah, I can do it this afternoon. Yeah.
Okay, great.
Cool.
Okay,
Thank
well,
you.
then tell us on the Zoom and we'll get
Yeah.
started, and let's tentatively plan to meet again on Tuesday. Okay, great.
Awesome.
Okay,
That's
excellent.
really exciting.
Yeah. Okay.
Thank you.
Very good. Thanks, everybody.
Yes.
Thank you.